morning, good afternoon, wherever you are in your day. As always, thank you for choosing to make general chemistry part of your day. I think this will be a relatively short and sweet video. We want to use bond energies to estimate enthalpy changes. Okay, so just to be clear, because normally delta is final minus initial, in this case we're going to do the opposite. There's a reason for it. It's because we're looking at bond dissociation energy, not bond forming energy, which is normally what you'd think of, so the signs are flipped. Just to reiterate, breaking bonds is a positive value, forming bonds is a negative value. And if you think about it from Hess's law, if we take the sum of all the bonds broken minus all the bonds formed, we should get our overall reaction then. There are a couple caveats here. Every carbon-carbon bond is not the same. Two very, very similar molecules, ethane and propane. Difference in the carbon-carbon energy, 377 kilojoules versus 370 kilojoules. That's a significant difference. So when we're looking at these values, they're average bond values, which means we can only estimate the delta H. Since this is an average with some air, we can estimate the reaction. Now, you're looking at maybe 5-10% air. I don't know how you feel about that. For most things, that's a pretty darn good estimate. If you could tell me what the revenue is for the federal government within 5% for the next year or their expenditures, you're probably doing a pretty good job. If you only had 5% air with the prediction for global climate change for the next 100 years, that would be fantabulous. So, take it all with a grain of salt. But if you really need to know what that number is, this isn't going to work. This will get you, ballpark. A very good ballpark, but, 2 sig figs. Okay. Let's just work an example. 2 ways to do this. One, the standard way is to estimate the overall energy change. The other way is if you have the overall energy change, you're trying to get at the bond energy of one of the pieces. Okay, so first thing you want to do, it'll be clearly spelled out in the word problem. Using bond energies, calculate either bond energy or calculate the enthalpy change. Easy enough. And they'll probably give you a table of bond energies with the problem. But if they don't, find the table in your book, ask your buddy Bob, back of the book, or Google, and find a data table of average bond energies. They will vary from source to source, so, I saw one where it's 495, one where it's 498 for this particular value. So there's a little bit of range. Again, it's an average value. So depending on what they use to average, they might get a slightly different value. Okay. Draw the Lewis structures for each of these. And this is where one thing that's going to be different from what we've done historically in this class. Is if there's 2, I want you to draw it twice. It may seem dumb, it may seem tedious, there's a reason for it, we'll get to that in a second. So I'm going to draw CH4, boom. I'm going to draw O2, yep. I'm going to draw CO2, yep. I'm going to draw 2 waters, boom, and boom. Okay. Next step is we want to count up all of the different bonds we have. And we want to be aware of left side versus right side. So on this side, I got a carbon to hydrogen bond, and I got 1, 2, 3, 4 of them. And if you lose track of what you're doing, well, as you're counting, check them off. So I got 4 carbon to hydrogen bonds. Oxygen, oxygen double, oxygen, oxygen double. So I got 2 oxygen, oxygen double bonds. So far, not that complicated, I hope. I'm going to do the same thing on the right-hand side. Carbon, oxygen double, 2 carbon, oxygen doubles. Then I got hydrogen to oxygen, and I got 1, 2, 3, 4 of those guys. 4 oxygen hydrogens. Or gals if you prefer. And then we're just going to go into our table and look up these values. And we're just going to change CH to whatever it says in the table. My table said 413 kilojoules. I looked up oxygen-oxygen double bond, and I got 495 kilojoules. I looked up carbon to oxygen double bond, and you got to make sure you pick a double when it's a double, and not a single or vice versa. And I got 743 kilojoules, and then I picked an oxygen to hydrogen bond, and I got 463 kilojoules. Now I'm just going to multiply through. We're going to take this side, and instead of this being an arrow, think of this just being a subtraction side. Add up this side, subtract this side, and we're done. So 4 times 413 plus 2 times 495 minus 2 times 743, and I'm going to distribute that negative through, minus 4 times 463, and I get a value of negative 696 kilojoules, and of course I should do what at this point? No, stop doing the happy victory over chemistry problem dance. Well, you can't do that yet. Just wait a moment. It's negative. Combustion, we're burning, exothermic, that makes sense. you know, maybe 700 kilojoules. Yeah, that seems reasonable. That's, you know, it's a small molecule, burning it, you know, I think maybe like a negative 1,000 or so. Sure, that all makes sense. Now, go ahead, do your victory over chemistry math problem, dance, celebration, and victory. And that's it for the math in this semester, I believe. We got one video to go. This was your penultimate video experience. Remember, for the ultimate experience, bring your tissues. Remember what Dr. Zeus said. Smile because it happened. Don't cry because it's over. You can always come back and watch these videos again. Peace.